We're going to move on to the subject of diffusion. When you're taught about diffusion in a chemistry or biology class, you're typically talking about diffusion of particles in a liquid. We're talking about diffusion of all kinds of stuff in a solid. We can expect, for example, if let's say we've got a pot full of molten metal, and if we drop in a drop of whatever, let's call it lead, if we drop in a particle of a little chunk of lead, do you think that that would over time diffuse throughout the liquid? Well, it would melt, and as the metal gets stirred around, then yeah, we could say that this concentrated bit of lead over time would sort of diffuse out, and we'd detect, an atom of lead here and there over time. So in a liquid, we sort of already know that that sort of event is going to happen. The trick is this same kind of phenomenon happens in a solid as well. So what is it that we might need to diffuse, or we might see diffusing throughout a solid crystalline structure? Well, this figure gives us some examples. You might have a small impurity. So this could be a single, as represented here, each of these spheres is an atom. This could be a single atom of some relatively small substance that sneaks in, and it kind of fits in between, in the vacant space in between this nice even crystal arrangement of what we're going to say are iron atoms. So if it fits in, if it squeezes into that space, it can kind of push the others out of its way a little bit, and we'll call that interstitial impurity. So interstitial just means in the unoccupied space in between things. If the impurity is, a couple of atoms together, then maybe it's much larger, and so that impurity may still be too large to fit and push things out of its way, but it's actually big enough that it's taking the place of one of the original iron atoms. So that is a substitutional impurity, because it's actually occupying the space that would have been occupied by an additional iron atom. We might have vacancies, simply the lack of an iron atom there, and one of the atoms in the material itself, which we're using iron as an example, it could be any crystalline solid. We might have what's called a Frankel defect, where it just, and to be fair, this diagram doesn't quite do it justice. It needs to be sort of trapped in the corner here. It can get wedged in between this one and that one, and that's a Frankel defect in the crystalline structure. And then, of course, we could have a self-interstitial atom stuck in the space between the normal arrangement of things, one of the iron atoms itself. So how do these things diffuse? Well, crystalline structures vibrate. All atomic structures shake around and move around. When we talk about the size of an atom, the size of an atom is made up of subatomic particles that are sort of zipping around and moving around. So there's a lot of movement implied, even in what looks like the most solid crystalline structure. The more we heat this up, the more energy we provide these atoms, the more they're going to kind of move around. Does it make sense, for example, to you that if I have an iron atom here and a substitutional impurity atom sneaks in, that this particular atom could get shoved into that vacancy? It could, right? Or maybe this atom here pushes on this one, and maybe this atom drops into that vacancy. Which means, atom number 1 drops into the vacancy, 2 now drops into the space formerly occupied by 1, and maybe 3 drops into the space occupied by 2.